high-level talking, but from a different perspective. And if there's going to be some time remaining, I'm going to talk about particular work of myself and my group that's not exactly related to carbon, but it's related to the modeling of the transportation system and electricity system, and really trying to think about how do you connect these two systems together. And there will be some implication of the carbon emission of these systems as well. All right, so let me start with the first part by giving you this figure. Okay, so this is the sources of the US greenhouse emission in the year of 2021. As you can see, transportation and electricity, they are the largest carbon emitters for the United States. And if you combine them, they are more than half of the total greenhouse gas emissions. Right. So now if I'm simply take a point of view of an engineer who know very little about carbon, about how do you capture, how do you do the sequestration and so on and so forth, I have this sort of simple and even maybe naive pathway to decarbonize these two systems. Where the first step is I want to decarbonize the electricity system, trying to replace all the fossil fuel-based generators or as much as possible with a renewable generation like wind and solar and so on and so forth. And the second step will be I would like to electrify the transportation system. I would like to replace the internal combustion engine vehicles with electric vehicles. Actually, about 2 weeks ago, I was in this NS workshop on exactly this topic of carbon neutral electricity and transportation. And it's an invite-only workshop. We actually have a lot of experts from the civil engineering department over the entire US, a lot of experts in the electrical engineering work on power systems. So we have a full room of engineers. There we are sort of looking at exactly the same picture that's presented. And the hope is that, well, if you look at the adoption of the electric vehicles and renewable generation assets like wind and solar, that's the ideal situation. We want the adoption to grow, and maybe at a certain point, maybe no longer the government need all the subsidies. You can have a mass market adoption, and it start to grow rapidly at some point organically. So a more realistic and more likely scenario is that when you grow this the adoption, when you grow the adoption of all this technology, at a certain point you are going to hit a break. Right. So what is this war? That really depends on some understanding of, for example, the power system. How does it work? Here at an extremely high level, I'm simply characterize all this, I would say, barriers into these 3 different buckets. One is so-called hardware. It's really about different generation assets in the power grid and how the power networks will work. Right. So we really have a sort of legacy power grid, in the sense that all the power network, they are sort of designed based on you have all these controllable generation plants, right? So, for the next hour, you want this generator to be able to generate this amount, you can just send this command to the generator, and generator will be able to roughly provide that amount of power. It's not designed for renewable generation like wind and solar. To some extent, their output is completely driven by the weather condition, right? So that's one of the things. Given the legacy grid, it's not very easy for us to really think about integrate 80%, 90% renewable. And then if you think about electrifying transportation, legacy grid also is inducing some barrier because, well, we don't even really have that amount of capacity, okay? So for the transformers in the power system, for the transmission line in the power system, you need to upgrade them to be able to support all the increased EV charging load. And of course, we also don't have enough charging infrastructure. So in the parking garage, I usually park where there are about, well, I would say hundreds of parking spots. There's only one charging connection, and a lot of time it's not working. Right. So that's the status quo right now. Right. So that's about hardware. All right. And then the second bucket I want to mention is, let me call it software, but it's really about how the grid is operated and controlled. So everything about how do you, so essentially the cyber aspects of the power system. So one issue is about how the grid is dispatched today. We really think about, well, for example, here we are in Indiana, and our transmission network is mostly controlled by Mid-Continent Independent System Operators, or MISO. And for MISO to operate this grid, they solve a large, complicated optimization problem. It's actually two different optimization, one unit commitment, the other one is economic dispatch. But basically, this optimization will tell the generator, hey, this is a collection of load, how much each of the generator need to be able to generate to serve all this load. Right, so all this optimization will factor in all the power network constraints and all the complexity in the power network. Right, so this optimization is not designed for renewable generation. Right, so like I mentioned, the key difference between the conventional controllable fossil fuel-based generator versus like wind and solar renewable generation is that the conventional generation asset can be controlled, while the renewable they are intermittent, they are uncertain. So you really have to, in some way, deal with the so-called stochastic resources. Now there are hundreds or even thousands of papers on this topic of how would you be able to incorporate stochastic resources. But if, for example, if you talk with engineers in MISO, in the system operating room, they would say maybe none of them actually work, or exactly how would you be able to incorporate all these methods in today's operation and make sure that the grid reliability is still maintained at a very high level. That's to some extent, that's a grand open question. So that's essentially the reliability in the operation timescale. Now, if you also want to think about reliability in the planning timescale, you want to be able to think about, hey, let's say we have 80%, 90% renewables, and all of this, their output is driven by the weather conditions. How would you make sure that if somebody turn on a large appliance which consumes a lot of electricity, some generator is generating that actual mode, right? So if you have like 100% renewable, there's no way. So you need to maybe have renewable plus energy storage. You maybe need to have renewable plus some fossil fuel-based generation, some dispatchable resources to make sure that you still have the reliability, right? In the planning scale. So that also imposes a lot of issues, right? And finally, there's also a lot of other economical and social and even behavioral aspects, which I'm not going to dive deep into, but there are other barriers as well. So, well, I was in that NSO workshop. We have a full room of engineers. We are looking at this plot. Everyone is excited. So we are trying to think about how do we break that brick wall, right? So how do we design better methods for the operation and planning? How do we really be able to scale up this, methods in the paper to the real world? I'm a little bit more pessimistic. The way that I'm really seeing this is that perhaps you don't only have one single brick wall, you have a bunch of bricks. Really think about all these barriers, they are actually a continuous process. In the sense that, for example, let's just think about the basic problem. You want to upgrade the grid to be able to support the electrified transportation, so essentially the EV charging load. It's a continuous process in the sense that you want to upgrade the grid that will support certain actual charging capacity, but that's a lot of investment cost. And then maybe you have more EV adoption, you have to upgrade again, and so on and so forth. This entire process, every single item requires millions and maybe even billions of dollars. And this is a continuous process over maybe 20 years, 30 years. And I personally believe that at a certain point, probably you are going to hit a steel wall, a wall that is just extremely hard for you to further push beyond, because really think about the last maybe 10% or 20% of, let's say fossil fuel-based generator, which are in place to make sure that you have reliable supply. How would you be able to completely replace them with renewable that's uncontrolled? If you really think about last 10%, 20% of the internal combustion engine-based vehicles, they probably need to be there. For example, let me ask you this question: would you like to electrify your ambulance fleet or not? Of course, you may think, okay, in normal operating condition, well, the EV ambulance probably will work the same as an internal combustion engine vehicle, but would you like to be reliable or responsible for, let's say you have some natural disaster and you have a great outage and none of your ambulance does not work, right? So that's the sort of things that potentially you need to think about. And by the end of the day, perhaps we are going to have some, I would say, healthy mixture of renewable generation and fossil fuel-based generation assets, and a healthy mixture of electric vehicles with internal combustion engine-based vehicles. So the takeaway message that I'm really trying to put here is that, well, for all this remaining fossil fuel-based generator and ICE vehicles, CCUS is going to play an important role. So CCUS not only is going to play an important role in this transition towards the end game, but also in the end game. Right. So that's the first point I'm trying to make. And actually, this is the last slide in the first part of this talk. And this is about the idea that Aleta and I have been talking about. Is really thinking about what potentially is a benefit for you to incorporate and connect the entire value chain. And here I'm giving you a particular example. And this example is about decarbonizing the electricity grid. So this is a synthetic example. I put the map of different states to just give you some indication about the potential implication and impact this thing could potentially have and the actual complexity in the system. So in this example, if you look at the black part, which is the above part, it's actually a very simple, what we call two-bus power network. You have a power network with two nodes. In power systems, we call these nodes as buses. So here I'm drawing in the state of Illinois, there's one bus representing all the load. And in the state of Indiana, there's another bus representing all the load. At each bus, there's going to be some demand, DIT. Okay, so that's actually the net demand. So that's our electricity consumption less the renewable generation. So the consumption actually vary over time and the renewable generation fluctuate a lot. So both of this demand, D1T and D2T, actually you think about they change dramatically over time for different time points in the day. All right. And then because I have lumped all the renewable generation in the net demand, so the remaining generation assets, G1 and G2, represent fossil fuel-based generators. All right. So the idea is that, well, let's say we are going to build all the carbon capture and storage systems for all this fossil fuel-based generators. What's going to happen is that, well, you can capture carbon dioxide at the generator G1 and G2 as well. And then you are going to transport the carbon dioxide to some carbon storage sites. Right. So let's think about a scenario. And it's a very, very straightforward scenario where we want to assume that let's say, the generator in Indiana is triple. And let's say it's always triple. Right, the way today power system operator dispatch this power system is that they are going to minimize the total fuel cost to serve some load. Now, if the second generator G2 is triple, what's going to happen is that, well, here I'm also assuming this transmission line is not congested, so you have enough capacity to send the power generated at G2 to the bus here, to the bus 1 here. So essentially what's going to happen is that all the load will be supplied by this G2. Now, this generator is producing all the power, it's consuming all the fuel, it's also going to generate all the carbon dioxide. G1 is not going to generate any carbon dioxide. But the consequence of that is that there's going to be a lot of carbon dioxide here, which have a quite long distance towards the carbon storage site. All right, so essentially you are going to have a very high carbon dioxide transport cost because of this simple dispatch, which system operator does today. Right, so I call this some form of passive integration in the sense that system operator does not think about carbon at all. They're just trying to minimize the fuel cost, and this is what's going to happen. Right, and there, of course, there's a different way of integration where you factor in the cost of fuel cost of generating for the power system. You factor in the cost of carbon capture. You factor in the cost of the transport and storage, and solve a joint optimization problem. This optimization is not hard to formulate at all. Right, and for this to work, you also have to really think about the spatial and temporal variability of all this demand process, because the demand, if the demand is changing over time or the dispatch result will change over time, that's going to impact the spatial and temporal distribution of the carbon emission on this map. All right, so the potential impact of this include, of course, you can save operation costs if you incorporate all the possible costs, including the fuel cost and the cost for the carbon system as well. But if you really think about long-term planning, actually there's a much more significant implication. For example, let's say if you want to build a new carbon storage site, would you want to build it here? That's close to today's carbon emitting source. But it's actually very easy if the system operator switch and change a different way of dispatch the power system. They can simply move all the generation to this G1. And if you build a storage, carbon storage site here, it probably does not make sense because the cost for transporting carbon from this class 1 to this new storage site probably going to be quite high. All right, so I see I'm running over time, but this is the last slide for the first part. And the basic takeaway message for this slide is simply integrating this entire value chain actually potentially have significant impact. All right, so let me move on to the second part, but let me do that at extremely faster pace and at a high level, so give you some idea of some of the ongoing work and what potentially is actually changing in the sense that when you electrify the transportation system and the electricity system, where these two systems will no longer become two separate systems, there will be a coupled system. So let me start with a motivating example, and that's really a personal example. So every day I wake up at home, I use electric kettle to boil hot water, I use microwave oven to cook breakfast. All of them consume quite a bit of electricity at home. All right, and then I'm going to drive my electric vehicle. It's actually a plug-in hybrid electric vehicle to work. So when I'm driving this electric vehicle, where I'm driving the car on the street, I'm contributing to the urban congestion. And if you're really into power systems, you also care about the battery inside of electric vehicles. So we would actually say this battery are mobile energy storage. They are energy storage on wheel in the sense that it allows this user to carry some amount of energy from point A, which is a home, to point B, which is a work. That actually has some implication for the power system. And then I arrive at work. Well, so the way that I do every day is I actually park at an illegal place so that I can get charging. But I do plug my electric vehicle to the charger, and that actually going to consume a lot of electricity at the workplace. So the takeaway message here is really, well, the simple act of driving an electric vehicle from home to work actually means three things. It means the vehicle flow and moving a car from A to B. It means the electricity or the energy flow. Think about the battery inside the electric vehicle and the energy it carries. It means the user flow, I move from A to B, move from home to work. And this user flow also implies the flow of electricity demand. Okay, so I was consuming electricity at home, and now I'm consuming electricity at work. So this is actually one thing, but it actually coupled all the three. So the central thesis of a lot of ongoing work in my lab is really trying to leverage this one thing to optimize the performance of the system that's tightly connected to it, including the power system, including the transportation system. And here I'm also, the reason I'm here, I'm also want to learn how would I be able to incorporate the power system, the carbon systems with this picture as well. So I think I don't have time to talk about particular examples, but I have worked on concrete settings where you leverage this observation, but design better ways for workplace charging and operate electrified fleets and electrified roadway as well. That's a new concept where we have an NSF engineering research center here working on that idea. So with that, I'm going to skip all the technical details and open to questions. Yeah,
I'm interested in what you say about electrified road. It's like, can you just give a high level description of that?
Yeah, so that's a technology. I guess maybe for some of you that might be science fiction, but it's actually gaining traction. We have this large engineering research center we have a lot of industry partners. What the concept is, when you are driving an electric vehicle, we put the actual charging pads within the pavement of the highway. So when you are driving the EV, we are charging that at the same time. Right, so we are actually building a prototype. It works. It's pretty costly, and we are trying to think about how would you optimize the cost with a system, that involve both operation and planning. Yeah.
Just a quick question. We're a little behind time.
Sure.
But don't they already have electrified systems in light rail?
Yeah, that's right.
Yeah.
So there's some small differences in the sense that if you have it's one possibility is that you have all the lights and then you have the overhead connection. And there's another possibility that you actually have the rail and the rail is providing power. And for this, it's like open to all the possible vehicles, as long as you have a compatible receiver on your car. Yeah, so that would work.
So there are people who even worry about transmission line causing cancer. You think that they put all these inductions in the road?
No, so exactly. So there's going to be a lot of challenges in terms of the deployment, and here, for this particular idea, it's still a concept that we are trying to test in terms of technical feasibility. How do you really scale it? How do we're actually building a pilot with the Indiana Department of Transportation. It's going to be a very short pilot. We first have to make sure technology work, and then we think about all the social, economical, and law issues. Yeah.